Amit Doegar. Yeah, let me introduce a brief profile about his experience and expertise. So, he is currently working with NITTTR Chandigarh, and before NITTTR, he had the experience while working in Bangalore as a software developer. So, to his credit, more than 60 publications in the international journal and conferences of repute. So, his research interest includes the ML, image processing, data analytics, open source technologies. So he has guided more than 70 master students for research in the different areas of computer science and engineering. So, sir, now you can continue the session, please.
Okay, thank you, sir. So here I have created one Google Classroom and I have uploaded the dataset, code and presentation you will get from this blog or the code and the Google Classroom I have joined here, given here. So now today's my talk is on federated learning. Like in the previous session, you have seen about the importance of federated learning. There are various technologies are there, and among these, today we'll discuss on the federated learning and the implementation of this. So you have seen that when we implement a lone blockchain, then its computational complexity is there. If we again implement GAN or LLM, they are again computationally expensive. So alone federated learning will also may not work properly because it requires the integration of these technologies. Once you integrate, then it will be difficult for the hackers to hack the machine. So now when we talk on the federated learning, we will see what is federated learning. So federated learning is a decentralized approach where multiple clients, devices, or thin clients, they can collaboratively train a machine learning model while keeping their data localized. What does it mean? Suppose you have the banking system, you have bank and you have multiple branches are there, and you want to find well related to some model related to cyber security, related to intrusion detection system. Okay, there is a comment here. Not only cyber security, this is a problem with many other fields. So that's why unassembled models will help. We find a model. So here, now you all of you will learn here how to implement this federated learning. What is the concept behind this? So you don't want to, without sharing the data. Let's say you have 5 sub branches. So without sharing the data, what you can do, you can train the model at the 5 different locations. Then you can send it to the central server, and then central server will analyze that model.
Sir, there is no voice.
Dear participants, the expert is trying to connect, so there is some network issue, so it will be recovered soon.
There was some disconnection at my end. I am sharing it again. So kindly confirm me. Are you able to see the presentation? Am I audible?
Yes,
Yes,
sir,
sir.
the presentation is visible and you are completely audible.
Okay, thank you, sir. So now why federated learning for threat analysis? So privacy preserving. Why? Because we are not sharing the data. So we can protect the sensitive user data. And we are using the decentralized data, leverage data distributed across the multiple organization or endpoints. And there is a collaborative threat detection can be done. So enable that entities to collaborate on threat analysis without exposing the proprietary or sensitive information. So what are the key use cases we can use using federated learning related to malware detection, maybe on various devices or mobiles or on servers without sharing the data. Intrusion detection system we can identify the unusual patterns in network traffic using federated learning. So I will demonstrate you practically regarding this intrusion detection system on multiple endpoints. Then detection on the phishing email, fraud detection, endpoint security. So in various cases. So what are the components of a federated learning? So there are four components are there. One is the clients, that is the endpoint or like companies devices, endpoint that hold the local data. Then we have the central server that aggregates the model updates from client and update the global model. Then we have the local model training that client train the model locally on their private data, and federated averaging. We combine the model updates from the client into a global modeling. So in the demo setup, we can have the Python libraries are available. Nowadays, various libraries are available. So like PyShift is available, like Flower. So those who are aware with the some of the libraries with Python, like Pandas, NumPy, scikit-learn, Keras. So here, a lot of libraries are available. So PyShift is there, that is integrated with the PyTorch. Then there is a open source flexible framework for experimentation. Then TensorFlow federated is there. Then OpenFL, open source federated learning platform is available. So in and also a lot of data sets are available. You can it's in available in the public domain, like NSL KDD network traffic for intrusion detection. Then there is another CICIDS dataset for intrusion detection, email phishing dataset, custom logs are available. Then we require the implementation step. So once we have the dataset, now I will show you the data. So that will give more clarity. So I hope you can see there are 5 files and one test file is available. So I'm going to train the federated model on this kind of data. So now I am opening this data. You can see. So there are certain numbers are there. So now what these numbers are representing. So I will show you in the presentation. So somewhere you can see in the last column, someone 1 and 0 is written there. So 1 means there it is an attack, 0 means it is not an attack. So you can see these are the labels are there, and we have these kind of data is there. Similarly, we have 5 files and we are using UNSW NB15 dataset. So we required to prepare the dataset. We have to split it across the multiple client to simulate decentralize the data. We need to define the model, maybe any machine learning model. So today we will discuss on the neural network, and uh, and the labels are classified as a normal or attack, that is represented with 1 and 0. Then we have to set up the federated learning, that is train the model. train the model locally on each client and use the federated averaging to aggregate the updates. Then we can evaluate the global model. So these are the certain simple example federated learning for IDS. We can import the libraries, we can implement random forest, we can do that training testing, simple like machine learning, and we have the clients. Then we have the uh, we can create the clients, we can run the federated learning server. So now in this implementation, we have used the UNSW NB15 training dataset that is now uploaded on the Google Classroom. So all of you can download. And so there are 5 training files and 1 test file is there. So now you have seen the this dataset in a file. So it has consists of 196 columns are there. So out of 196, from 0 to 195 are the features. What type of features are there? Like related to network traffic characteristics are there, flow, duration, destination, IP, protocol, source, etc. And the last level, you have the 0 for benign traffic and 1 for malicious traffic. So if we see little more detail of about this dataset, it consists of the basic feature like IP address, protocol, service type, that duration, start time, end time of the flow. Content features are there, number of bytes, packets and flags, average packet size, flow bytes per second, statistical features are available. Then we do the pre-processing. We apply the min-max scaler to normalize the features or machine learning. And also we use the time lag data. So used for time series analysis by reshaping the data into a sequence of historical traffic patterns. So now how this labeling has been done, there could be a question how it will identify whether it's a normal benign or normal traffic or a attack or malicious traffic. So there are these tools are available. So this traffic is labeled based on the attack categories. So there are denial of service attacks, backdoor attacks are there, exploits are there, exploiting vulnerabilities in the software, or fusers are there. These are the tools that generate massive network packets to find the vulnerabilities. So using this has been classified, and on this we are going to implement one of the machine learning model, that is a neural network, and then we will do for the federated learning, and we'll do the feature analysis. So now what is the uh, model definition on neural network? We have the input layer, we have the output layer, in between we have the hidden layers with ReLU, sigmoid or softmax we can use to handle the non-linearity in the model. So now we have to train the clients locally on the subset of the data, and then we will do the aggregation. Now I'm going to start opening this. So I'm going to use the Google Colab. So there we are training the clients locally. Then we update the combine to improve on the global model, and finally we get the training loss and the accuracy. So we can get the evaluation parameters in terms of accuracy, precision, recall, and F1 score. So what are the steps for implementation? So first we need to have the libraries like NumPy, TensorFlow. Then we need to load the dataset. And after loading the dataset, we will do pre-processing of audit, like if there is any outliers are there or any missing data is there, we can perform the process. After pre-processing, we can split into training and testing set. And then we define the model like neural network architecture that is suitable for IDS. We have implemented this. And then we set up the federated learning. So here we are going to simulate multiple clients with local data sets, and then we are going to perform the aggregation for combining the local model updates. And then finally we do the federated training and get the final evaluation and results. So if we see again the summary of the Python code, so first we are going to do the data pre-processing, then we are going to define the data model. Here we are going to use the CNN with layers, multiple one-dimensional convolution layer. So let me now open here. So now I'm opening here the Colab, and here Now it's opening here. Now my data, I have uploaded my data in the Google Drive. So let me here. So we will define the model here. Now before execution, let me show the. So this is the client one. Here you can see. So after reading the data, now here we have the clients. So we can define the various clients. So here let's say this is a location one, client one. We can define client one. So here we are defining the model. We are passing the training and test data, and here we have defined the uh, convolutional one-dimensional neural networks, and then we are compiling it and we are getting some weights. So you can see here we are saving the weight and we are saving as by the name server one dot weights. Similarly, at second client, at client number 2, we are doing in the same way and we're saving the weights. And now in this example, we have taken the 5 clients. So client 3, and you can see we are again, after performing this, we are saving the weights. Same we are doing with the 4th and 5th node. So this is a client 4 and this is a client 5th. So after that, once the weights are ready, then we are going to load the models, and we are collecting these weights in this variable. So we are going to store in a variable, and then we are doing the performing the averaging of the weights of the loaded model. So what is the final execution of this code? So this is the final execution of this code. So now we are giving some epochs. Maybe for demonstration I have taken 3, but we can take up to 10 or 20 or 30. So what is the meaning of epoch? We are sending the entire data set through the model. So that means we are sending 3 times. So here we are collecting model 1, model 2, model 3, model 4, model 5, and this is the code for the federated averaging and evaluation learning. So if we see this function, what we are doing, we are getting the average weights, we are building the model, we are evaluating the model, and we are saving the centralized model. And in building the model, what we are doing here, we have defined the one model and we are compiling it and we are set the average weights. So before running this code, this is the entire code. I will run it again step by step. So this is the flow of the code. The same thing is represented here. What we have done, we have defined the convolution neural network with layers, multiple one-dimensional convolution neural network for feature extraction. We have used a dense layer for classification and output the prediction using the sigmoid activation function for binary classification. We have set up the federated learning setup. We have simulated a distributed environment with multiple clients. So in this example, we have taken 5 clients and each having their own local data set. And we are not sharing the local data set, we are sharing the trained model weights. Then we are doing the federated averaging, that is nothing but the aggregate the weights from locally trained model using the federated averaging mechanism. And we can build a global model with the average weighted. And then finally we are evaluating the and saving. So finally the output training loss and accuracy we will get. So now what are the observations in this demonstration? So you will find federated learning ensure the privacy with good detection rates, and we have discussed and its application to the ideas, and it emphasizes on the privacy preserving techniques, and there are certain challenges like in the previous session also communication overhead, and clients could be heterogeneous in nature. So that is a challenge. And what are the future scope? Differential privacy and optimized communication. And this is one of the challenge, communication overhead, heterogeneous data. So you are handling the non-independent and identical distributed data across the clients, and security concerns. So if any of the node get compromised, then security concerns could be there. So that's why uh, federated learning alone may not give the appropriate result. So you have to integrate with the blockchain kind of technologies. So one can have the differential privacy or homomorphic encryption to enhance the privacy. So what are the real world application of this federated learning? So cyber threat intelligence sharing, or like malware analysis on the mobile, collaborative learning among organization, decentralized fraud detection, cross-industry collaboration, endpoint security is there, and protecting the edge devices through federated learning. And what is the current scenario now? So now this federated learning continue to evolve with various application in the various fields like healthcare, finance, and smart devices. So we can do collaborative diagnosis, diagnose the models across the hospitals without sharing the data, and fraud detection without sharing the sensitive transaction data in finance, or even at the enhance the personalization in IoT devices or smart devices. So what are the future directions of this federated learning? So like in we have the deep learning, we have the transfer learning. Similarly, we can have the have advanced techniques like federated transfer learning, personalized federated learning, and scaling the federated learning system and handle millions of devices through this technology. Now I'm going to demonstrate this example. So kindly confirm me, are you able to see the font size, or shall I increase the font size? So now what we are doing, we from google.collab, I'm going to bind the drive with my uh, this Python notebook code. So I'm going to run, I have to authenticate it once. So what is the code from google.collab? Import the drive, and then we are going to use the drive.mount content drive. So now once we run this, we need to connect to the Google Drive. Now I'm giving my email access. So now we can verify because it's a Linux platform, Ubuntu. So we can use a Linux command to see the content of the file. So I'm going to use a ls content drive, my drive, collab notebook. There I have created one folder. So now you can see these are the files are there, which I have shown you in the Excel. Now we are going to create the directories to save this file. So here I'm going to create the one data, one server, one central server. And now these three directories has been created. Now I want to copy all my content in this data directory. So now I have copied the content, entire content in this uh, directory, and we can verify it. So now these 6 files are ready to train. So for each client, so like client number 1, I'm going to use this file. So let me annotate you. So now I have 5 clients. I have 5 clients. So for client number 1, I'm going to use this file. For client number 2, I'm going to use this file. Client number 3, this file. Client number 4, this file. And client number 5, this file. So once we train the model, after that, we are not going to share these data. We are going to share the weights. So we will share the weights, learning weights. So we'll see now step by step. And also we required one local code file. So under here, this is a Python file, customized Python file. In this Python file, there are 2 functions are there: load CSV and data set preprocessing. So we are going to now read it, and we are setting the filter warnings, ignore any kind of warning. So you can see now it has been uploaded. If you don't want to use the Google Drive, you can upload through this function also from google.colab import file, and you can upload these 6 files. So now what is the meaning of this TL? As I told you, so this is defined how much historical data is considered for each prediction. So input shape of the model in the input layer, and TL specifies the number of type steps or sequence length expected by the model. So now we can read. So now what we are going in these variable, we are going to read these file. What function we are going, either pandas function we can use, or using the load CSV. So these are the files, these are the in these variable, and we are going to load, and then we are similarly we are now training the data. We are setting the scalar. Now as we know how many columns are there, 196 columns are there. So in this it will have all 196 columns. Similarly in the row and column, all rows. So what is the meaning of this first symbol? All rows and columns 0 to 196. And then we have the test data, and then we are using the min max scalar. So we are going to now we are going to transform for all the data set. So we are going to normalize this using the min max. So this is the inbuilt part of the Python, and then we are reshaping this so that these are the variable. Now you can see train 1, training x train 2, we are reshaping it. Similarly, we are reading the data set and doing the reshaping. So after that, now these are the labels. So what does mean? All rows and which column number? 196. So we have now 5 data. This is only for the data preparation in one goal, or you can do separately also. So now there are 5 clients are there. What we have done, we have for 5 clients, we have created the 5 files in one go. So we have now our data is ready. Now we are, after this, we are defining one function load models, and in this we are reading the weights of all the models that we are going to train. So this function we will call when we are going to build the model. So there we are going to call this function load models. It will compile and it will get the weights. So now we are going to define the neural network architecture for IDS, or you can use any model, any machine learning architecture or machine learning model that simulate, and we are going to simulate multiple clients with the local data sets. So in this demonstration, we are going to use the 5 clients. So you can see the code of the first client, same with the second, third, fourth, and fifth. And we are passing the training data and these parameters. Here we have defined the model sequentially. We are compiling and we are ensuring that consistent data shapes. So we have defining the sample here, X train and Y train, and we are training the model. So using the model.fit, we are passing the training data set with that consists of training feature, training labels, and we are specifying the batch size, epochs, validation data, and we are saving the weights. Same we are doing with the saving the weight for second model. So now one by one, we will run. So I'm running for client number at client side. Now it has been run successfully. So now we are going to try with the client second. So at the second node, so same we are going to with the third node, fourth node, or fifth node. So in this way, you can run the model locally and you are saving their weights. And this is the client fifth. So now you can see the 5 weights are ready. Server 1, server 2, server 3, server 4, server 5. And now we are defining the load the weight of all the models in the server directory. And here we can verify also. So if we see here ls, so you can see there are these folders are available. Now if you see here colon ls data, so under that you can see these files are available. And if you say here ls server, you're listing the content of the server. So now as soon as we call this function, all the weights you will find will be under the server. Now we are calling this function under the federated learning averaging model. So now we are going to average the weight of the loaded model. We are calling this function load the weight of all the models and check whether the model has been loaded successfully or not. So here we are getting the number of layers in the models and iterate over each layer. So now we will run here, and after running this, again we can verify, and then we are going to build the model. And now after building the model, we are going to evaluate the model. So we have called the different functions and we are saving the model in the central server. So again, now if you see here ls server, so nothing is there because actual code is here. What is the model? This is the main model. This is the main, we can say, main federated learning model. So you are defining the model, and what you are calling the average, and inside the average already we have load the model, then we are building the model with the average weights, and then we are evaluating here and saving the model. So finally, now what we have done so far, I am repeating here. So now in this scenario, we have selected 5 clients at different locations, and so now this is the client 1. We have defined the model and we have saved their weights. So in TensorFlow, this is the inbuilt function model.save underscore weights. And if you only say dot save, it will load the architecture also and weights also. So we are interested only in the weights. So these are the numerical values or the training parameters, we can say. Then similarly in the second client, here we are saving with the what is the name, server2.weights.h5. Same with the server 3, server 4, and server 5. And after that we are load the model, and then we are performing the federated learning averaging, build the model, and we are evaluating the model. So now finally now here this is the train the model in federated setting for multiple epochs, show the loss and accuracy model for after aggregation. Now we are calling these models here: model 1, model 2, model 3, model 4, model 5, and we are calling this function federated averaging and evaluation. So now we will run it. So now you can see, and k.clear sessions means it will clear the Keras background session. So now it is now training and running here. So now I advise all the participants, you can download right now and you can try to run it once, this code. And if there is any issue while running, please inform. So go to the Google Classroom, download the file by the same name, Atal underscore federated computing ideas. It is in the Python notebook. or .py and download the dataset, upload and run it. So you can see now it is running for 3 iterations. So you can see now FL model is ready. Again it is testing. So now you got this score. So you can see here first score is related to the next is about the accuracy, first one is for related to the loss. So you can see 69% and 44%. So loss you are getting 0.69 and accuracy you got only 44 in first iteration. And now we will see in the second iteration. So you can see here. So in second we got accuracy of 70% in second iteration. And finally in the third iteration or third epoch, now it is running for all the fives, doing the aggregation and so you have noticed in the first epoch it gave only around how much accuracy, around 44%. In second epoch it has given the accuracy 70%. And now the model is ready. So now you can see around 90% accuracy you have got in third iteration. And you got the score of with the loss of 0.22%. So now these are the 3 epochs. So you can verify now here LS server. So you can see now these are the weights: server 1 weight, server 2 weights, server 3, server 4 and server 5. So only with the help of weights you have trained the model. So same you can see in the Python code. If we see what are the steps are there. So we need to have some libraries. We have import the essential libraries. So what are the libraries we have imported here? So you can see here. So here we have used the sklearn for doing the pre-processing, normalizing using the min-max scaler. We have used the keras to import as a backend as K. We have import the TensorFlow. From TensorFlow, we have import the keras and our custom method to load the CSV and do the pre-processing. And after that, we have done the dataset loading. So we have load the dataset, perform the pre-processing and split into training and testing set. So here you can see we have defined our dataset is in the data directory. So we have defined the path, and after that we have using the load CSV, our customize function. We have read this file, and then we have now we got in the 5 variables the data from all rows and all columns, and then we have performed the scaling min-max scaler, and after performing the min-max scaler, we have reshaped to the in this format, and then we got the label in the training data in all rows and this column. Now after that we have performed the load the model For weights path in the model, we have applied the model tensorflow.keras.sequential model, compile, and in this array we have append the model. Then we have defined the neural network architecture for different clients. We can have multiple any model. So in this demonstration, we have used a neural network model that is a convolution first one-dimensional. So here we have implemented the filters, kernel size, activation functions, and then we have compiled the model. And after compiling the model, we have saved the weights. So that is under the server directory name, under the name server1.weights. Because we are only interested in the weights from various clients. Similarly, we have done for the second client, and same with the third and fourth and the last one client. That was our fifth client. So now we got the 5 weights. So these 5 weights will send it to the central server, and there we will apply the federated learning. So in federated learning, we do the federated learning averaging of this. We build the model, we evaluate the model and save the FL model. So now here we have the TensorFlow NumPy. We load the model, and it will return the NumPy array representing the weight of each across this one. And then we can define average the weight of the loaded weight under this function FL underscore average. So it will return a list of NumPy arrays representing the average weight for each layer. We will check if any model were loaded. If not, then return it, else get the number of layer in the model and iterate over each layer. Then we define the build the model. So here you can see we have built the model. Then we have evaluated the model. In evaluation, we got the we have passed the test data set, and we have defined the batch size, and we print the score here. Then we have defined the we have saved under central server. So final model weight is under FL model.h5. Not because it is not weights, but it is a save. So complete architecture you will find here and the weights. And what is the working flow for main federated learning model? So we define the model federated learning. We are getting the average weights. We are building the model with average weights, and we are evaluating the model, and we are saving the centralized model. And then finally we train the model in federated setting for multiple epochs. That will show the loss and the accuracy matrices after aggregation. So now in this way we got, and under server we have these weights. And if we see about the under ls central server. So now this is our model is there. And if you want to see what is the size of this model, so ls minus lsh central server. So here we can see the size is only around 676 kilobyte. So we can see that is approximately 673 kb. So this is a final model, and where we have the architecture is included in this, and using that we can we can share this model with everyone. So just they have to use the TensorFlow or Keras library, and they can load the model, and they can further implement or analyze it further. So now any participant has any doubt, question, query related to federated learning? So I hope now you got the idea. So now we'll revise, and then we will conclude the session. So now we understood that it is not a centralized approach, it is a decentralized approach where multiple clients can train at their own machine learning model while keeping the data localized and secure. they need not to share the data. Only the model updates, that is the gradients, are shared with the central server, ensuring the data privacy. And FL federated learning approach trains the model across multiple decentralized devices or server without sharing the raw data. What are the benefits? Enhance the privacy and security, enable multi-party collaboration. So what are the core techniques are there? Differential privacy and federated averaging. And why it is being chosen? So because traditional machine learning involves sending user data to the central server. So that is a privacy concern. To avoid that, using the federated learning allows the training model locally on the user device, share only the model updates and not the raw data. Okay, there is a question, how can it be used in any healthcare application? So in healthcare application, you may have the data maybe of 5 hospitals or maybe 10 hospitals. So again, on the 10 hospitals, you have to run the model on different 10 hospitals, and you have to save the weights, not the, and you need not to share the data. So you will have the 10 different files that consist of the different weights on different hospital data, and you will share it to the centralized server or federated main machine. So what it will do, it will collect all those 10 uh, weights or 10 files and then further analyze that. So like in the code you have seen, we have done on the 5 clients, like here, if you see here. So, so now you can see. So now at the client number 1, or like in hospital number 1. So now you are training the model, and this is a data train 01, train 01 test dataset. In this way you are sending. These are the parameters, and how you got this, you have already now this dataset I have done in a one goal instead of doing on the separately. So now you got the training data for client 1 or for hospital number 1. Same you have the data for set for the hospital number 2 up to 10. Then you will make the model ready. Like in this case, I have used the uh, uh, CNN architecture or neural network architecture, or you can use any machine learning model. Then you can save the weights. Like here, we are saving, and we are here you can see in each of the machine at the different locations. Like here, client number 1, what you are doing, you are saving the weights using the model.save weights function, and you can give the appropriate name, and you can save either directly or inside a folder. Like in my case, I have created one folder. Inside that, I have saved the weights. So if you want to see, similarly, we have done for the second client. If you see under the server, you will find all these weights are there. Server 1 weight, server 2, server 3, server 4, and server 5. Now, what we'll do after these 5 weights are ready. So we will load the model. We will say we'll define the function. And now you can see here, server star.weights.h5. We are match the weights file pattern. So you have server 1.weights.h5, you have server 2, server 3, or client 1, client 2, client 3 up to client 10. So you are initializing an empty list here, array, and you are aggregating here. So now after the aggregation, you are like using the function append, because this is inside the loop. So we have given here the indentation. So inside this for loop, it is appending the weights. So append the weight of the each model and return the list of model weights. And then you can, so now which function you have used? Load models. and you are calling this function here under the averaging. So now when we are doing the this federated learning averaging the weights of the loaded model, so you can see the function here. First, it is loading the all the weights in which variable model underscore weights, load the weight of all the models. So now all the weights are in which variable, it is under model underscore weight. And then you are checking getting the number of layers in the model, and you are iterate over each layer and returning the average weight. So under here we are reading the models and we are getting the weights using numpy.mean. So we are using the mean and we are getting the average of those weights, and we are appending the average weight for the current layer to the list of average. So that is undergoing under average underscore weights. So now this, after this, we are going to build the model. So here we are building the model. So again, we are defining the uh, deep, this convolutional neural network in one dimensional. And here we have set the average weight. So now we got the average weight of all the models. So now our federated learning model is ready. Here we can write here federated learning model is ready. Model is ready. We can return the model and we can define a function to evaluate the model, save the model, and finally, when we are defining the model FL, so it is calling all these functions: average, build model, evaluate model, save FL model. And this is in which what is the main model? We can say here model, or we can give the appropriate final federated for better clarity learning model. And we are going to call this model. So model final, it is a federated learning model. Model underscore final federated learning model. And we are going to call here. So here we will define here. So now federated averaging and evaluation. So in this loop, we are calling these. So we have defined these models, and we are actually it has to run in the separate nodes because of the limitation of the online platform and other things I have shown in the same Python notebook. So now we are calling this model final dot federated learning, because in federated learning you are concerned with the weights, not with the data. So in that way we are going to save this. So whenever you define or changes anything, you have to run it again. So if you give now some more epochs, you will get more better accuracy. So now if you try this, so you will get in a better way. So now there is a question, could you send the collab link? Could you find, so initially now I'm sharing again, already it is uploaded. So that's why I put some slots so that all of you can try. Go to this blog, join the Google Colab, Google Classroom. You will get the presentation, you will get the data set, you will get the code also. So you can download and you can try. If still we have some time, it will not take, if you have good bandwidth, it will not take much time. So there is another question. You will get the dataset code and every presentation also. So how can adversarial attacks compromise the privacy guarantees of validated learning? Like in the previous session, you have seen, because nodes are at the distant places and they have to communicate. So during communication, if any node get compromised, then adversarial attacks, they can compromise the, or any other attack, they can compromise the privacy guarantee of validated learning. So we have to very ensure. So that's why blockchain or some strong encryption techniques or HTTPS over, we have to make it very secure. So if there any attack or any compromise happen during the communication naturally, because what is the main objective of federated learning? Otherwise, this purpose will fail. So now I will show you again with this diagrammatically. So now what is the purpose here? We have 5 nodes or 5 banks or 5 hospitals at different locations. So what they have the data, and they have the plus some kind of ML. Same here, D data plus M in each remote location. Data plus, so you are training the data plus model at the local end. Suppose now we are using nowadays antiviruses. So what they're doing, they will scan on our machine and they may send us that analysis to the remote machine, remote server, or maybe in mobile. So if we don't opt this federated learning, and this is the main server. This is the main server here. You can do the same thing without federated learning also. In that case, you have to send your data. You have to send your data, and in that way, you are sharing your data, and that may cause the privacy concern. So like in your mobile, there is some malicious code is there, or some kind of attack is there, IDS is there, intrusion is there. So either you have to share your entire data of your mobile, or you can train at your end and only share the weight. So instead of that, instead of this approach, in federated learning, what we are doing, we are getting the weights. So weight 1 at this location, weight 2 at this location, weight 3. So in our code, we have done server 1 dot weight name we have given, server 1 weight, server 2, server 3, like this. You are have the weights. So you are sending the weights here instead of data. So that's why federated learning preserves the privacy concerns, because you are not sharing the data, you are sharing only the weights. I hope now it is clear. So you are sharing the weights on the main server. So if you see again on the code, so now here what we are doing, we have 5 clients, client number 1, client number 2, client number 3, 4, and we are saving the weights under this directory server 5 dot weights dot h5, and we can verify it also using the ls command under server folder. What are the different files are there? So now it's running, and you will see here it will show all the 5 weight files. Okay, there is another question. Can federated learning be extended to cross-domain threat analysis? Yes. If you have noticed in the presentation, what are the future scope of this technology? So these are the challenges are there. Communication overhead, because they are at the different locations, and security concerns are also there, and there is kind of heterogeneous data could be there. So in real world application, we can use this technology for threat intelligence sharing, collaborative learning among the organization. So what they're sharing only the weights, and it could be used for decentralized fraud detection, cross industry collaboration. It can be used definitely, endpoint security. And what are the current state of this technology in healthcare, in finance? Not only these, in various, you can do the collaborative diagnosing model across the hospital, fraud detection without sharing the transaction data. and enhance the personalization in IoT. What are the future direction you can go for? Federated transfer learning, personalized federated learning, scaling is another field, and handling millions of devices using this technology. So now we have the billions of mobiles are there. So using the federated learning, we can analyze, is there any kind of malware on the mobile devices, or is there any cyber security threat is there? So because they are also they are preserving the privacy, because they are not sharing the data. So on the all millions of devices, just you are running the your algorithm or model, and you are getting the weights from the millions of devices, and then further you are going to analyze it. So same here, you can see. So under ls server, now you can see these are the weights are there. So let me annotate it once more. So I hope all of you got the code. So you can see here. So this is a weight, server 2, server 3, or whatever the appropriate name you can give. So these are the weights. And after getting the weights, we are doing the federated learning averaging, build the model, evaluate the model, and save the final model. So finally, we have saved the model in the directory under here. You can see finally we have saved here central server, or you can give the appropriate name. So if you see again under ls central server, so now, oh sorry, we have to give ls and the directory name central server. So now this is the final model. So you can also rename it final federated learning model. So you can save it in this way also. So now I hope all of you got the code, all of you got the data set. So now I will upload this presentation also now, because there was some minor changes were there. So now that was not there earlier. So here you will find the course material for the previous session also, cyber, and you can get this code. And in this is a code one working. If you are running on the standalone, you can run in this way also, data free. And now I'm uploading the presentation. So now you will get the presentation also, code is also there. Under this data.zip, you have all the 6 files are there. And later on also, if you got any doubt, question, query, you can put the query here, and we'll try to answer your question. So whenever you will put the question, automatically it will come to our email, as well as we will see here, and we'll try to reply you. So anyone is trying to implement now? Anyone has any doubt, question, query? Okay, there is a question from Dr. Nagarajan. How can federated learning improve the detection of zero-day threats? Because zero-day threats are those threats which does not have the pre-trained signatures. So like in if we have the predefined signatures of that, only then we will able to match. But zero-day threats happen then using the certain tools. Like I have told you, we have to see the anomaly. If there is any zero-day attack happens, zero-day attack or threats means it does not have any previous history. It's a new kind of attack. So we can see, we can analyze with the anomaly in the like if you see in the previous session, we can find the traffic, what type of traffic is there, how much resources are they, and let me show you, you will get the idea. So here, now if you see the network traffic patterns, I hope now your machine is ready. Let's say your machine is ready. Can you see the duration, protocol, source IP, destination, source port, destination port, packet, byte count, and we are labeling. So let's say insert, shift cell down. So let's say this is I'm putting just for to save the time, some kind of protocol, source IP, some destination IP, source IP. Let's it's a 0-day attack, and we have to identify whether it's a attack or normal. So what we have to do, we have to match that particular packet information with our existing model. So it is just like a, that's why machine learning or AI techniques are very good for 0-day attack, because 0-day attack is like a unknown sample. Like when we train the model in any machine learning, we have the training data, we have the test data. Test data is unseen data. So that's why we have to train the model, and we have to ensure our model is neither doing the overfitting or underfitting. Now, what is the meaning of overfitting? So we have the training data, we have the training data, we have the unseen data, or also known as test data, unseen data. So it's just like a 0-day. So what is the meaning of overfitting? In training data, you are getting 98% or 99% accuracy, and in test data or in unseen data, you are getting let's say 80% accuracy. So that difference is known as overfitting. That means your model has uh, got the data from the noise. And what is the meaning of underfitting? Both the accuracy of training data are lesser, like 80% or for training, and let's say 75% for the test data. So we have to avoid this overfitting. So how to do? We have to train the model, and in case of cybersecurity, accuracy must be above 99%, and we have to do many iterations. We have to do uh, we have to fit the model with the model fit with the optimizers, various optimizers, or also known as fine tuning, fine tune the model, various hyperparameters. So a lot of scope is there in research. So once our model is there, so when there is, whenever there is any 0-day attack or unseen data attack, easily it will be able to recognize. I hope you got the idea. So training part is very important, and how you are defining the model and architecture. So any other question, query from any other participant? Uh, are you able to download the dataset code and presentation? You may run maybe later on. Are you able to download? You require Gmail account to join the Google Classroom. Okay, there is another question in cybersecurity. How does federated learning help monitor multi-organization network activities without exposing sensitive data? Because yeah, we are not sharing the data, because that is the crust, that is the thrust, and that is the main objective of the federated learning. So in multi-organization network activities, we are not sharing the data. What we are doing, like let's say there are 5 organizations are there at different locations. So we are training the model there only and sharing the weights, not the data. Okay, someone has asked about the, please share again. Okay, you go to this blog, you will find Google Classroom links are there. Google Classroom links are there. Join the Google Classroom and download the dataset, presentation, and the code. So anyone has downloaded the dataset, code, and presentation? Anyone has any issue with the downloading? So you can run easily in the Google Colab, because if you upload using simple file uploading, it may take time. So it is recommended to first copy the dataset, because it is in MBs. So you copy the dataset in your Google Drive. From there, directly you can fetch the dataset and then proceed further. So now any question, any query from any participant? Okay, if there is no question query, so shall we close the session? Okay, there is a question. What strategies are used to handle communication latency in federated system? This is more related to the communication latency. So uh, now you can see, let's say you have here huge amount of data, like here in my case, if you see, you will get the idea. Latency will be less. Why? Now, if you see the data set here, this is the data set, and I have used the 5 files. And in this file, you can see, if I do the annotation again, you can see the size of the first file is 39 MB, second file is 17 MB, third file is 19 MB, the data is 17 MB, 19 MB, and 13 MB, 33 MB. So if you total do the sum of these, you will get around 40, 60, 90, around more than 100 MB. So let's say in real scenario, in various location 1, let's say take an example of 3 locations, location 1, location 2, and location 3. Let's say you have 10 GB of data. Here again you have 10 GB or more data, and here you have 10 GB or more data. Now when you train the model at this location, at this location, and at this location, you are not sharing the data. What you are sharing the weights of your train model, and it is in few KB or maximum it may be few MB. So like in my case, if we do the total of this, it is it may be around 150 MB. It is around 6 files are there, and it is around 150 MB. So you are sharing only the weights. So now if you see here again the size of the weights, here, so I am using one switch ls minus l asset. This is a part of the Linux command. Why we are using Linux command? If you see, if we run the command, the what type of distribution we are using on Google Colab, it is Ubuntu. Ubuntu 22.4. It is a one variant of the Linux. So any Linux commands can be run here. So now you can see the size of the weight machines. It is only 1 MB, around 2 MB. Again, this is a 2 MB. Again, this is a 2 MB. Again, this is a 2 MB. And sixth one is again 2 MB. So you can see drastically from 100 MB. Now the total from 100 MB, we got only 3, 4, 5, around 10 MB. From 100 MB, we got only 10 MB. And if you see the size of the main model, that central server, after further it's training, only it's in KB. So in this way, automatically, because we are sending the not the data 10 GB that may take hours. So just we are sending the what we are sending only the weights. So because of that reason, uh, it is going to reduce the latency in the federated system. Okay, there is a question how to avoid overfitting. Okay, so now when we talk, I hope you got the idea of overfitting. So overfitting means there are two problems with any machine learning problem: overfitting and underfitting. So with the training data, you are getting 90% accuracy, and with test data or unseen data, you are getting uh, 75% accuracy. So that is the overfitting. So that means it is learning from the noise. And what is underfitting? You are getting the both accuracies low. So you are getting the both accuracies as low. So let's say in training data, you are getting 80% accuracy, and in test data, you are getting 70% accuracy, low. So now there are various strategies are there. There are various strategies are there. Like in the previous class, we have seen the value of patience we can give. Now, what is this patience? So when you're training the model, there are certain iteration and epochs are there. Certain iterations and epochs are there. So there are three concepts we have discussed in the previous class. So one is the batch size. Let me batch size. Another is the number of iterations. Number of iterations and epochs. Now, what is the meaning of this? So let's say we have 100 students, and then they want to visit to 3 labs. So in one lab we can accommodate only 20. So batch size will be 20. So how many iterations it will require to visit to one lab? How many iterations will take to visit one lab? It will take 5 iterations, 20, 20, 20, 20, 20. So total iterations will be because they have to visit to 3 labs. So 3 into 5. How 5 came? 100 divided by 20. 100 divided by 20. Because 20 can go on. So iterations to visit one lab is equal to 5. Total iterations will be 15. And how many epochs are there? Epoch means when entire data set pass through the model. When entire data set pass through the model. So there now in this case epoch will be 3. I hope you got the idea of this. Now how to reduce the overfitting? We are giving the concept of patience. So if you see in the code, and that code is also available in the Google Classroom, and along with the data set that is on section 1, section 2, and here until session on 31st December. So if I show you simple here, so you can explore this. There is a concept here, epoch and patience. Now what is the meaning of this patience? You can see now here we have defined the layers. I hope it is visible to. Now here we are giving the criteria early stop. And we have given patience is equal to 3. Now what does it mean? And this is also we have defined the parameter epochs and batch size is a method to model the field and play a vital role in machine learning. Now epoch is referred to one complete pass of the entire training data set. If you have 50 epochs, that means 50 times you are sending the entire data set or to that model. And overfitting if the model trained too much on the data. So if you are giving so many epochs, so you should not give the so many epochs. That is the one criteria. You should give the optimal epoch. How to decide that? You can give the patience value. Now what is the meaning of this patience value here? if you compare and create the patience value, so it will check continuously for the further 3. For example, let me explain here. So now you have given, let's say, patience value is equal to 5. So in one of the iteration, you got the accuracy. You have to find the loss. So let's say loss is 6%. We are talking about the loss. So our objective is to minimize the loss. In iteration 1, the value of 6. In second iteration, let's say patience is equal to 3, and the loss is, let's say, 5. In iteration 2, okay, it's good. Then again, there are multiple iterations will be there, and in iteration 3, let's say 4. Now in iteration 4, let's say again now it's 6. In iteration 5, let's say it's 5. Iteration 6. So there is no improvement. So have you noticed? There is no improvement. It is not going in the lesser way. So automatically it will stop. So instead of going to iteration 7, it will stop. Let's say you have given here iterations 100. Iterations as 100. So instead of going to the 100, you have given here patients 3 or 5. So it will keep on looking for further 3 or 5 iterations, and it will notice, is there any improvement? Let's say, okay, there is an improvement here. Or let's say you have given here patient's value as 5. And in iteration 7, again 5. In iteration 8, in iteration 5th one, let's say 3.9. So it will continue because it is going to see the further 5 iterations with reference to the previous one, So here you can see it is decreasing. So again, suppose it does not decrease, and again it is 4.1, then it will stop. So that is the one criteria. Then we have the dropout rate, and you can go through these papers with the code.com. Now, because we have the scarcity of time, so if you go to this website, paperswithcode.com, you will get the data set. You will get the browse state of the art techniques. You have 12,368 benchmark data sets. These many, more than 1,50,000 papers are there. These are the data sets are available, and these are the methods are available. So whatever problem you are working for, let's say GAN or on or any activation functions. So what are the activation functions are there? In our case, we have used ReLU, sigmoid, and it was introduced in year 2000. Then GLU, Gaussian error came. Now what are the latest? You can click here and you can see CAN, Contacker, HEL, and other activation functions are also available. And how many are available? So you can see these many are available. So switch, you might be aware, those who are working with the machine learning, like we are using 10H, Licky ReLU, PReLU. So all these activation functions, not only these, but other technologies are also available. So there are various techniques. Regularization is another technique to reduce the overfitting. So how many methods are there in regularization? Dropout, as I told you, that was proposed in 2014. Normally we drop out 64%. Weight decay, that was proposed in 1943. L1 regularization, L2 regularization. I hope you can, or otherwise you can click on that particular item. And latest methods are LVR, early dropout, band dropout, weight reset. All these techniques are there to reduce the overfitting. So any other question, query? We can have one or two more questions if local coordinators they uh, allow, could suggest funding agency in cyber security projects. Many are there. You see the DST, or you can put the same question in the Google Classroom. If you are part of the Google Classroom, or later on you join, we will provide you the list of the funding agency. So there are many agencies are there, and even there are certain projects are available for research scholar from Microsoft, from Google, from Amazon. A lot of scope is there. So sure, we will suggest some funding agency in cyber security projects. Okay, there is a question which with recent trends such as 5G, even 6G, people are talking on 6G, edge computing, and AI-driven network optimization. How can these technologies work together to further reduce communication latency and enhance real-time applications? So as I told you, whether you are using federated learning or not, at least you can get the weights, because the purpose is to solve the problem. So using the, once you get the weight, like instead of sending the 100 GB data or terabyte of data, like in medical scenario, we have different modalities are there, and we have in data in terabyte. So instead of sending the data to some other location, we simply train the model there itself and send the weights. So now you have seen in our case, we had around 150 MB data and we got only 10 MB weights from 5 nodes. So in that way, that is a one way, and you can at least for your research purposes, you can justify you are sending the weights only. Whether you are adopting this federated learning or not, at least you got the idea, because the purpose, main thing, you have to focus on the purpose. So your focus is on the optimization, the and reduce the communication latency. So in that way, you can see from 150 to 10 MB. Okay, please suggest. So again, I hope we have constraint of the time, and there are various very good questions are there. We are happy to see the enthusiasm and the questions. Please put on the Google Classrooms also. And please suggest topics where the collaboration of federated learning with cloud computing is possible in various. There are like if you just open this code, I will share the link, paperswithcode.com. So you will see more than 1 lakh papers are available, methods are available under this. So please explore this. This is not only the source, but IEEE, they have also, I'm forwarding the name now. They have also, you will get the benchmark papers, open source paper, and number of topics where the collaboration of federated learning with cloud computing is possible, very much possible. So now what you can do, you can have problems from various remote location, and you can apply the federated learning, five remote machines or 100 machines, or let's say 1000 remote machines. So you are getting the weights, and you can upload with cloud computing. There you can apply, or you can also propose federated learning as a service. Now platform as a service, we have software as a service, we have, so you can propose this federated learning, and now you understood, you can just run the code, and you understood how to any kind of data set you can easily convert into weights, and this is the optimized this, and there is a readme file is also there. The main author information you will get on GitHub or GitHub, so you can further analyze there. That I uh, pasted the entire code of the that particular person, and the modified code, optimized code, because that was developed in with the Python 3.6, and now there is a latest version is Python 3.14, and Google Colab use Python 3.10. So when we have different versions, so we have the compatibility issue. So on Google Colab, it will run very without any issue, without any problem. Can you repeat the question? Can you repeat the question?
Actually, sir, I believe some participant has unmuted himself by herself by mistake. So thank you so much, sir, for the wonderful session.
Thank you, sir. Thank you.
Sir, your session has provided us with a deep understanding of the cutting-edge advancements in the federated learning and its pivotal role in ensuring the privacy while analyzing the cyber threats. So, participants, I am confident that the knowledge and insights shared during this session will be significant to enhance your understanding of this emerging discipline and open up the new avenues for research and applications in your professional endeavors. So, once again, I thank you, Dr. Doeger, for for taking up the time to share your knowledge with us, and your contribution has undoubtedly added immense value to this FTP. So, thank you so much, sir.
Thank you, sir. Thank you for giving the opportunity. Thank you.
Thank you. Right.
So I thank again all the participants for patience listening and for interaction. Thank you. Thank you, one and all.
Right.
Okay, sir. So shall I quit now?
Yes, sir, you can leave.
Okay, thank you.
Thank you. Dear participants, the feedback links are shared in the chat box. So you are requested to fill both the feedbacks for the session 9 and session 10. And tomorrow session schedule is different. So as shared in the plan, in the WhatsApp chat as well, in the email as well. So the schedule is will start from the 2 p.m. on tomorrow. So kindly join the schedule on time. So there are three sessions on tomorrow, 2 to 3:30 p.m. and then 3:30 to 5 p.m. and the last session will be from 5 p.m. to 6:30 p.m. So thereafter the online test and feedback session will be taken from 6:30 to 7:30 p.m. So the mode duration will be conveyed in the in on tomorrow, and we wish you all the best for the test. If anyone has any query, he or she can unmute himself herself, or can drop the query in the chat box. So the appropriate resources are already shared in the important document section of the Atal web portal. So the quiz in the form of multiple choice questions ranging from 30 to 40 questions. So that will be conveyed exactly on tomorrow. So that the multiple choice question the candidates has to appear for.